Welcome to this series of Foundation Chemistry Lab Talks. This session we will look at the lab which is titled The Effects of Hydrogen Bonding, as you can see here. Now the aim of the exercise is to relate hydrogen bonding to volume change on freezing, the temperature change on mixing solutions, volume change on mixing solutions, and also to relate hydrogen bonding to the solubility of certain substances. Before we actually go into the experiment, we would look at some of the background material that would introduce this topic of hydrogen bonding. I want to look at intermolecular attractions, the concept of intermolecular attractions. And as you can see here, there are three known types of intermolecular attractions. The first one is the dipole-dipole forces, as it is called. And this is the one that exists in polar molecules, and that is really due to the partial positive and negative charges that you find on these polar molecules. Now, an example is given here, hydrogen chloride, and the molecule of this diatomic substance is given here, and this is the partial positive end, and that is the partial negative end. These charges arise because of the different electronegativities of these two atoms. We know that chlorine is more electronegative than hydrogen, so the electrons will tend to come around this end here where chlorine is, and thus leaving this end more positive. So we have this kind of situation. This is really a dipole, and it will have a dipole moment. Now down here we see the molecules of hydrogen chloride. That's one molecule of hydrogen chloride. That's another molecule, and that's another molecule, and another molecule. And there are many of them in a solution of hydrogen chloride. And I've shown here the attraction. Right? As you know from your physics that negative and positive charges attract each other. Right? So we have the attraction between this dipole and that dipole. The negative end and the positive end. Likewise, this negative end gets attracted to the positive end of this other dipole, and so on and so on. So these attractive forces that exist in this manner is what we term as dipole-dipole forces. We're shown here that the strength of these dipole-dipole forces is about 1%, the strength of the covalent bonds. The next kind of intermolecular attraction is what is called London forces, and this is most prominent in nonpolar compounds. It's found, or you can see this effect in nonpolar compounds. In fact, this actually exist in all kinds of compounds, but because of the presence of the other much stronger forces, like the one we just looked at, dipole-dipole forces, and the one after this, which is termed hydrogen bonding, this London forces, the effect of the London forces is masked by the other stronger ones. How does this London forces arise? If we look at this end here of the illustration, in any atom, there is a positively charged nucleus because of the presence of the protons, and the electrons move around, and it's the constant motion of these electrons that give rise to what is known as the instantaneous dipole, which is shown on this end, and the red arrows here try to indicate that the electrons are constantly in motion. If we picture this atom here moving across, approaching another atom, right? And this atom has, for instance, at that particular moment, electrons on this side or this end. Then as this atom approaches the other one with the electrons on this end and here on this end, it will induce or it will create the repulsion. And so these two electrons, or the electrons, will tend to move over to the other side. Okay? And that is what is termed as induced dipole. Right? So here we have a situation where we have instantaneous dipole and induced dipole. So London forces is really the combination of these instantaneous and induced dipoles, as we can see here. It is comprised the instantaneous and the induced dipole forces. So this is the attraction that we find between these kind of dipoles, instantaneous and induced. Right? So the attraction forms and disappears only to form again a few moments later. So what happens is the small short-lived dipoles cause what we can call momentary tugs, right? And these are the ones that exist between these dipoles. And note that these sort of attractive forces are very weak. So the London forces are relatively weak as compared to the first one that we saw. Now the third kind of intermolecular attractions that we will look at is what is more related to what we are talking about today, and that is what we're going to look at in the experiment. And this is what is termed as hydrogen bonding. Now, this is really a special case of dipole-dipole attraction, and it exists when you have hydrogen covalently bonded to one of the electronegative elements, or atoms like nitrogen, fluorine, and oxygen. Now, there are two reasons are given here for this hydrogen bonding. First one is, as given already, the large electronegativity difference between the two atoms, hydrogen and one of these elements here. The other one is the small size of the atoms involved, right? And this gives rise to the change at the two ends, which is highly concentrated. The strength of this hydrogen bonding is much stronger. It's about 5 times stronger than the first kind that we looked at, the dipole-dipole attractions. Just to illustrate further the effect of hydrogen bonding, I have here a graph that illustrates this bonding. Right, on this axis here we have boiling points, and on the horizontal axis we have the period number. Right, in this small box you can see the groups. That's group 4, group 5, 6, and 7 of the periodic table. If we look at the graphs that are drawn here, for instance, let's look at the first one, carbon, silicon, and germanium. Now these are the elements that we find in group 4, carbon, silicon, germanium. You should remember from what you've learned that as you go down the periodic table in a group, the size of the element increases. And because of that, the size of the element increases. Because of that, the boiling point should also increase. Right, here we are looking at the hydrides. And if we look at the hydrides of these elements, carbon, that's this one here, CH4, and silicon tetrahydride, this one here, germanium hydride, we see that they follow a trend, right, where methane, in this case, the carbon hydride, is the lowest, followed by silicon, and then germanium. We said as we come down, the boiling point increases. So that's okay for this group. Now, if we move on to the next group, group 5, nitrogen, phosphorus, and so on, we see that that is where nitrogen or ammonia should be, the hydride of nitrogen, right? This one here, and the next one is the phosphorus one. Then we move up to arsenic and antimony. Right? We see here that the actual boiling point for ammonia is not down here, as indicated by these dotted lines. Right? It is up there. Right? Now, when you come to the next group, which is oxygen, sulfur, and so on, Again, for the higher elements, you find that they follow the trend, that is increasing boiling point. But for for H2O, water in this case, the boiling point is right up there. Okay? It doesn't follow the trend. The same thing with HF, which is up there. Okay? So the question that you may ask is why this deviation from the trend, right? And the answer to that is simply because of hydrogen bonding, right? You find that there is hydrogen bonding in these molecules here, in water, right, hydrogen fluoride, and in ammonia. And this is the cause of the increase in boiling points in these three. So the deviation from the trend. Right, in this experiment, you're going to be looking at this hydrogen bonding, the last type of intermolecular attraction that we've considered. And so we go through the procedure as given in your lab manuals. And I'm just going to highlight some of the important points, important things that you need to observe or to concentrate on, to emphasize. All right, so the first one, part one, unfortunately there is no title for that first part, but I've given it a title. You may like to put in that title as volume change on freezing. Right, in this first part, you're asked to take 5 cm cubed of each of water and cyclohexane. Your two liquids or two solutions are water and cyclohexane. And you're going to put them in separate boiling tubes. All right, some of you may be wondering, what is a boiling tube? So a boiling tube is really just a large test tube like this. Okay? Now this may be the test tube that you are used to, this smaller size. The boiling tube is just a larger version of it. Okay? So that is a boiling tube. So you take 2 of these and you are asked to put in 5 cm cubed of each of these solutions, water and cyclohexane. Right, you don't really need to measure the volume. Okay? If you don't have a measuring cylinder, don't worry. As long as you put in the, right, this is water here, and let's say I'm putting in a volume of that water in this boiling tube. Okay? That may be more than 5 cm cubed. Now, what you need to do is to mark the level of this water. Okay? So here I have a marking pen that I can use, and you mark the level of that. Okay? Now, if you don't have a marking pen, what can you use? Right, you can use anything that you can grab your hands on, sellotape, masking tape, okay? A strip of it along there, as long as you know where you're starting from. Okay? So this is what we're going to be doing in the first exercise. That's water, right? And then I need another one for cyclohexane. Right, this is the cyclohexane solution, and you can just put in again a similar volume. Right, and again you need to mark that level. Right, the other thing that you may want to do at this stage is also, identify your tubes. Okay? So this is cyclohexane. You may like to put a C on that to indicate that this is cyclohexane, and okay, the other one, just put H or W, whatever you like. All right, so we got our 2 solutions there in the boiling tubes, and we need to place that in a freezing mixture. Right. Some of you may be wondering, what is a freezing mixture? The freezing mixture is simply ice cubes. Okay, I've been having this ice sitting for a while, so that's what I'm going to put in this basin. Right, some of that ice is already melting already. Right, freezing mixture. We will use some of this sodium chloride, right, salt sodium chloride, to put in that. This is just to lower the freezing point of this. So you just add that to the to your ice, and then you will take your two boiling tubes. You take your two boiling tubes, and you will place the boiling tubes in the freezing mixture. All right. Now, something that's very important here, I'd like you to note, is that you will notice that I have these two boiling tubes upright, right, vertical. That is very important because if you have it slanting, then you won't be able to see your mark or to use that mark that you have placed. Okay, so the tubes should be vertical, right, upright in your freezing mixture. Right, so we will leave this for some time, and we'll come back to that freezing mixture with our two solutions in it. All right. So while that is solidifying, freezing, we will move on to the next part, okay? And then we'll come back to that after we find that they are frozen. Right, part 2 talks about volume change on mixing. Volume change on mixing. Right, in this second part, you are required to pipette 25 cm cubed of water into a measuring cylinder. Right, so we have our measuring cylinder here. Now this goes up to 100 cm cubed, and we will need a 25 cm cubed bulb pipette. Right, so that's our pipette, and of course you will need your pipette filler. Okay, I discourage you from using your mouth. Right, so you're going to pipette 25 cm cubed of water, distilled water or just tap water. And after you've done that, now I'd like to show you how to do that. Okay? Now it's very important here that you measure the volume accurately. That is why we are using a measuring cylinder. Right? Sorry, not a measuring cylinder, a pipette. Now you'll notice that these pipette fillers are not very well designed, and they don't seem to work most of the time. So what you can do is you put the tip of the pipette at the bottom, and then slowly remove your pipette filler, and then with your finger on the tip of that pipette, you slowly take the volume or that level down, okay? Keeping your eye on the mark on the pipette. Right, so there we are. Right, it's there. Now you take it out here and put it in your measuring cylinder. Right, let it run down freely. So that is the way to pipette the 25 cm cube of water. All right, so I've got it into there. Now the next one is pipetting 25 cm cubed of cyclohexane. Now it's very important that when you're using chemicals, that you protect your eyes. So you may like to put on your safety glasses if you have one. The first one was water, so that's not too bad. Now I think I can do the pipetting, but the whole thing that I'd like to show you here is that you need to do it properly. We can do the same thing again with this solution and put it in here, right? So you can do that. I'm sure you shouldn't have any problems with that. The thing to do at the end of this exercise is to note the final volume, right? Note the final volume in your measuring cylinder, okay? You need to note the final volume. You know that 25 plus 25 is 50, okay? So is the final volume 50.0? Is it less than 50, or is it greater than 50? Right? So that is the whole point of this exercise. And then you are to interpret your result in terms of hydrogen bonding. Okay? So first of all, you need to know what are you putting in there. Is there hydrogen bonding in those solutions? And if there is, then what is the effect of that hydrogen bonding? Is it causing the volume to increase, to decrease, or to remain the same? So that is something that you need to do. All right, let's just check our part 1 and see whether we've got any frozen solid here. Okay, this is the one that I label C, right? C for cyclohexane, right? Now you can see already that this is frozen. Didn't take too long. Okay? This is already frozen. You can see a solid there. That's your mark that you put with your pencil pen. So you can judge yourselves whether the level has gone down, whether it's the same, or whether it has increased. I leave that for you to judge. You can see that this other one, water, is still in the liquid state. Might need a longer time or more salt. Okay? Right. The point that I like to emphasize here for this part 1 is when in number 3, procedure 3 says warm each in a water bath. Right? You can have a water bath if you like. Now, but for the cyclohexane, the warming doesn't really need a water bath. Okay? It only requires heat from your hand. Okay? You can just warm it up with your palm of your hand, and the idea is to melt that solid so that it is about 3/4 left. So we will do that. I'm just using the heat from my hand to do that. Right? So this is a cyclohexane. With the water, right, you can use the warm water bath, okay, or even a burner if you have a burner. Right, you can see that it's already melting. Right, that solid that we had initially starting to form into a liquid. Okay? So I like you to observe this because this is a very important point that you need to observe. Right? So let's give it more heat. Right? You can see that it's moving more freely now. You keep looking at that solid. Right? What happens to it? Now, some of you may be saying, "Oh, yeah, it is floating." Okay, it's floating. Yes, it is floating. You should also try and see why is it floating. Right? You will notice that there are bubbles, okay, coming up from the sides. There are bubbles. Now, what I'd like you to do is to observe that solid until the very last bit of it. Right? And then that should form your observation, right? What you need to write down for your observation. So see that solid and watch it until the last bit of it disappears. So we can say that it is still floating, all right? It's becoming smaller and smaller. And we could still see the bubbles of gas. All right, something interesting happening now. Okay, so I think you have seen what's happening. Huh? Now, you should be able now to note down your observations and then try and relate this observation to hydrogen bonding. Is there any hydrogen bonding in this solution? Right, if there is, what is the effect of that? Or if it is not there, right, why is the solid initially floating and then coming down? Right, and the same thing with water, but I'm sure you're much more familiar with water. Okay, you've had ice cubes added to your cold drinks and so on. So this one is not a problem. Okay, once you get that solidified, you just warm it up and see what happens. So that is how you should finish off with part 1, to try and note the visible differences between the two solutions and relate these differences to the presence or absence of hydrogen bonding. Right? Now, the next one, part 3, talks about temperature change on mixing. Temperature change on mixing. So we are going to mix two solutions, and we're going to first of all measure the temperatures of these two solutions, and then mix the two and take the temperature again. Right, so you're asked here to take about 10 cm cubed of samples of ethanol and cyclohexane. right, ethanol and cyclohexane. I'm not going to do the whole exercise, but what I'd like to point out to you, right, that is a test tube that you can use. Here, once again, because it's ethanol, we need our safety glasses, right? 10 mils, you can measure that with your measuring cylinder if you have one. That's ethanol, okay? So you need a thermometer to take the temperature, right? So you place your thermometer in that solution, about that much, right? And then it's important that you let that, mercury stabilize, okay, before you take your reading. Now, it's very important that you have your eye, the same level with the mercury, okay? Not down there or not up there. All right? So that is how you measure your temperature. So this is what you're going to do. You note down the temperature for this ethanol solution. All right? Then you're going to take another 10 mils of cyclohexane in another test tube. You measure the temperature of that as well. And then you can pour one of the or the other into the other one, and then take the temperature again. All right. When you mix the two solutions, the temperature might decrease or might increase. Okay. All right. That is something for you to observe. But what's important is that you keep your eye on the mercury and make sure that if it is rising, you wait until it stops rising. Okay. It stabilizes, and you take that temperature. If it is decreasing, you wait until it stops decreasing, and that's your final temperature. Okay, so that is something that you can observe. Right, so that is for ethanol and cyclohexane, and you can do the same with ethanol and ethyl acetate, which is the other mixture. Right, and the final part to this exercise is solubilities. Part 4 talks about solubilities. So we are going to test the solubility of small amounts of solutes. The solutes are listed on the left-hand side of that table in your manual. And you want to test the solubilities in the different solvents that you are provided here. The solvents are water, methanol, and carbon tetrachloride. Right, what's important at this stage, I'd like to, first of all, remind you about the terms that you're going to be using. Now, the terms that you want to recall are soluble and miscible. Soluble and miscible. Right, we talk of a solid, right, being soluble in a solution, okay, or in a liquid. And if you're using a liquid to add to another liquid, then the term is miscible. Miscible if it mixes, immiscible if it doesn't mix. Okay? So those are the terms: soluble for solids in liquids, and miscible for liquids in liquids. Okay? Right. Column 2 in your table talks about the nature of solute. Right. For that, you can mention, or you can write down the state, whether it's a solid, a liquid, right? Whether there is hydrogen bonding present or absent, whether it is ionic, polar, or non-polar covalent. Okay? So those are the things that you can put in the nature of solute column. All right, so I'm not going to carry out all these exercises, but I just want to demonstrate to you how you can do this exercise. For example, the first one is to test the solubility of sodium chloride in water, in our first solvent, water. Right, sodium chloride is what we have here. It's the same salt that we use for our freezing mixture. And water, right? Water is this one here in the in this wash bottle. And for this, we should be really using micro test tubes, right? These small size test tubes. Okay, we just want to see whether it dissolves or not. All right. So you use very small amounts. Okay, if that is your this is your first solvent, water. So we add a small amount of that. And to add your salt, if you have a micro spatula, okay, use that, right, that amount there Just add it into there. And the way to do it is you don't put your thumb here and shake it. We discourage that. Okay, you shake it this way. Okay? That's the proper way to shake it. And then you should be able to see whether it dissolves or it doesn't. Right? So like in this case, sodium chloride, we can see is quite soluble. Right? Now, if you are using another liquid, right, let's see, okay, cyclohexane is one of the liquids here. So we want to see the solubility, sorry, not the solubility, the miscibility, using the right term. Okay, so that's water, right, and we want to test the miscibility of this. So we need a dropper, right, that's our cyclohexane, and we only need to add a few drops of that cyclohexane. Okay, into our solvent, in this case water. Right, add a few drops, and the same way that you did before, I just tap it like that. Okay, so we can see that we have a layer on top, and that layer won't go away, it remains. So the two liquids in this case are immiscible, right? Cyclohexane and water. So that's how you test the solubility of these substances. All right. Yeah, and so you can go on and do the rest of the exercise. Now, at the end of this this practical, you have post-lab questions. Right? Post-lab questions. There are 4 given here, and the knowledge that you have gained through the introductory part and the the practical that you have done should enable you to answer these post-lab questions. Thank you.